So we are now ready to introduce the complete definition of integrability of an integral of a function which needs not be non-negative. So let f be a measurable function, so with values in r this time, not r bar. Then we'll say that f is integrable with respect to mu if the integral of the absolute value of f against d mu is finite. So you see now this, you already know what this is because the absolute value of f is a non-negative function. So this integral is the integral for non-negative functions. So if this quantity here is finite, well, we will say that f is integrable, and we will be able actually to define its integral. How do we do that? Well, it's given by this very important equation. We will say by definition of this quantity here, so the integral of f d mu for any measurable function with values in r which satisfies this is the integral of f plus d mu minus the integral of f minus d mu, where f plus, I've already introduced this notation before, f plus is given by this formula and f minus by this formula. Let me draw a quick picture which should help you to understand what I'm talking about. So let's say f is a function. Okay, let's make an easy picture like this. And well, f plus here would be this function in blue. This function in blue. So it's equal to f when f is non-negative. When f is negative, this is equal to 0. And when f is non-negative, this is again equal to f. And the same goes for f minus. F minus is equal to 0 here when f is positive, and then it's equal to f when f is negative. Okay, so this is f minus, and this is f plus. It's just a simple notation, and you see that what's interesting in both cases is f plus is non-negative. Of course, this is a non-negative function. This is a non-negative function. So this is well defined as an integral of non-negative function. Same here. And what's important now is that we don't subtract to infinities. So this assumption here, I will explain why it's here. It implies that this is finite and this is finite. So if both are finite, it's just the difference of two finite numbers, everything goes well. But if the case could happen where this is infinity and this is infinity, and in that case, this difference does not make sense. Okay, this we want to avoid by imposing this condition. So what is happening actually is that, observe that the absolute value of f is equal to f plus f minus. Okay, so in fact, this means that f plus or minus is less than or equal to the absolute value of f. So the integral of f plus or minus d mu is less than or equal to the integral of the absolute value of f d mu, which is finite. Okay, so this quantity, which is obviously non-negative, this integral here is finite. So this quantity is finite, this quantity is finite, and the whole difference makes sense. Okay, so that's how we define the integral in general. We will denote the space. Actually, we won't use much this notation, but just temporarily, we define the set of integrable functions, and we denote it like that with a calligraphic L1, to say actually that the power here of integrability is 1. We'll see LP spaces very soon. And we have some properties which are again very important for us when we define an integral. We need to check that these properties are actually true. The first one is the triangle inequality that we will prove. The second one is that this space is a linear space, and that this is just the linearity of the integral is still true. We have the fact that if f is smaller than g almost everywhere, then the integral of f is smaller than the integral of g. And if they are equal almost everywhere, then both integrals coincide. So how do we prove that? I will only give you perhaps information on the first, or maybe the first. Okay, so proof. How do we prove that if, the triangle inequality? Well, the integral of f d mu, which is a finite object. So this is by definition equal to the integral of f plus d mu minus the integral of f minus d mu. And by the usual triangle inequality, this is less than the integral of f plus d mu plus the absolute value of the integral of f minus d mu. But, like I said, this is a non-negative function. This is also a non-negative function. So in fact, both integrals are non-negative, so you can remove the absolute values. So this is actually equal to the integral of f plus d mu plus the integral of f minus d mu, which is equal to, by linearity, integral of f plus f minus d mu. Okay, and like I said, this is equal to the integral of the absolute value of f d mu. Okay, so we have the triangle inequality. For the second point, well, you will do it as an exercise if you want. The third point, which was yes, that if f is less than g, then the integral of f is less than the integral of g. We've already done this trick, so integral of g d mu is equal to the integral of f d mu. This is by linearity. Okay, I'm using the linearity of the second point, plus the integral of g minus f d mu. This is non-negative, so the whole integral is non-negative, and you get 0.3. For 0.4, well, if f is equal to g almost everywhere, well, that implies, you can check that, you can verify that this implies that the positive part of f is equal to the positive part of g almost everywhere, and same for minus, right? And therefore, well, I'll let you conclude, and you have proven your 4 points. Okay? The most, perhaps one, or with the monotone convergence theorem, one of the most important results of integration theory will be the dominated convergence theorem. So usually in English it's more frequently called the Lebesgue theorem, and it goes like that. So assume that fn is a sequence of integrable functions, so there is no assumption of monotony here, and assume that fn of x converges, fn converges to f mu almost everywhere. So that's the first assumption, and the second assumption is, well, of course, the dominated assumption, which goes like this. There must exist some function g, which absolutely do not depend on n, which is integrable. Okay, so it's non-negative. It's not in R plus bar, right? This quantity has to be finite. And for any n in capital N, fn is less than or equal to g mu almost everywhere. So if these 2 points are satisfied, then we deduce that the limit, the pointwise limit here, is integrable, and that we can interchange the order of the integral and the limit. So limit of the integral of fn is equal to the integral of the limit of fn, which is f. Okay, we have actually slightly more than this. This statement is slightly stronger. It's what we call convergence in L1. Let me just remind you what mu almost everywhere convergence means. It means that, okay, so fn converges to f mu almost everywhere means that the set of points, the measure of the set of points where fn of x does not converge to f of x, the set of points where this bad event happens has measure 0, right? Which, by the way, you can check that this set here is measurable. Right, so let's prove this this result, which is again something very satisfying. It's not as elegant as the proof as the monotone convergence theorem, but you'll see we can prove it rather easily. So I will make a slightly stronger assumption first. I will assume actually that these properties, these two properties, they hold not only almost everywhere, but actually everywhere. And then I will see how to go from this assumption to the general one that is here. So first assume, first point, first assume that these two sets of assumptions, so y I prime and to I prime, which says that, so for any x in E, fn of x converges to f of x. So this is pointwise convergence instead of mu almost everywhere convergence. And assume that for any x in E, the absolute value of fn of x is smaller than g of x. Okay, so from I prime, we deduce that fn, sorry, from both, we deduce by taking the limit that f of x is less than g of x. So actually, the integral of f d mu is less than the integral of g d mu, which by assumption is finite. So we deduce actually that f is integrable. Okay, so that's the first thing to notice. Besides, there is, and that's where I used quite, I mean, that's a very convenient trick, and it will make it possible to do a very quick proof. So there is, observe that there is fn minus f, which is by the triangle inequality, this is less than fn plus f, which is smaller than 2g. And now I will use Fatou's lemma. So here is how I do that. So for Fatou's lemma, I need non-negative functions, which is why I notice that 2g is bigger than fn minus f, because now what I can do is say that the limit, so n goes to infinity, of the integral of this function, so 2g minus the absolute value of fn minus f against d mu, is, so by Fatou's lemma, this is bigger than the integral of 2g, well actually 2g minus the limit of fn minus f, which is 0 because I have pointwise convergence. So this is bigger, actually just bigger than the integral of 2g d mu. Okay, and now what follows is that the integral of 2g d mu minus the lim sup of, as n goes to infinity, of the integral of fn minus f d mu is greater than, sorry, I should have precised, okay, is greater than the integral of 2g d mu. So why is this true? Because actually this just, okay, this quantity here, which is equal to this one, okay, because I just use the linearity of the integral here, so that gives me integral of 2g minus integral of fn minus f, okay. So now I apply the limit, but the first term, integral of 2g, does not depend on n, so that gives me just integral of 2g d mu. And now I have also the limit of minus the integral of fn minus f, and the limit of minus something is equal to minus the lim sup. So that's a small trick that you can verify. So we have this inequality, and you see that on both sides of the inequality, well, I have the integral of 2g d mu and integral of 2g d mu, from which I deduce that the lim sup of integral of fn minus f d mu is less than or equal to 0, and as a matter of fact, of course, this is also non-negative, so like this. So in the end, what I have is an equality here with 0. Okay, so I've proven this this convergence. Okay. Because from the fact that lim sup of this thing goes to 0, I can also deduce, it's an exercise for you, because here this is 0, so I can deduce, okay, let me write that the limit itself, not only the lim sup, but the limit, I let you think about why this is true here, the limit of fn minus f d mu is equal to 0. Okay, so we have proven this convergence, and this implies this convergence. So I let you check why also this convergence here implies this one. So now, how do we see that this works for the general condition? So now consider the general assumptions of the theorem. So small I and small two small i's. So general assumption of the theorem. We will define some auxiliary sequences. So define E tilde to be the set of points in E such that fn of x converges to f of x, and such that fn of x is less than g of x. So by assumption, because we have almost everywhere convergence and the fact that almost everywhere fn is smaller than g, so by assumption the measure of E minus E tilde is 0. Okay, so you can define now fn tilde and fn as follows. And you will see that if I define them correctly, my goal is that fn tilde and fn, they satisfy 1 prime and 2 prime. So fn tilde will be defined like that. Fn tilde equals to fn on the set E tilde. Okay, when I say that, that means that on the complement on E minus E tilde, f tilde is equal to 0. And same for f tilde, which will be equal to f on E tilde. Okay, in particular, fn tilde is equal to fn mu almost everywhere. F tilde is equal to f mu almost everywhere. And fn tilde and f tilde, they satisfy now 1 prime and 2 prime. Since, okay, we have seen before that two integrals, I mean the integral of functions which coincide almost everywhere are equal. So since fn tilde d mu is equal to the integral of fn d mu, and the integral of f tilde d mu is equal to the integral of f d mu, and again the integral of fn tilde minus f tilde d mu is equal to the integral of fn minus f, the desired result follows. And we have proven this very nice theorem, which probably you've encountered it in a probably different form before, but I doubt that you were ever able to prove it, while here it's quite reasonably simple to prove this result. So now we will face a very important difficulty actually in the theory of integration against measures, is the difficulty to define norms. So let me explain. Here are some other spaces that we can define. We've defined L1 already, calligraphic L1. We can do the same with, so defining LP for finite P greater than 1, always greater than 1, like this. So say that the set of functions which are measurable and such that this integral is finite, the integral of the power P of f, which is finite, and this is a vector space. You can do the same with L infinity, saying that it's a set of measurable functions which are bounded by some C for mu almost every x. But the problem is, okay, I would like to define a norm now. I have a vector space, okay, I would like a normed vector space. And the difficulty is that this thing here, it has nice property, as we will see. Okay, it's homogeneous. It satisfies the triangle inequality. We will see that. It's not obvious from this expression, but we will prove it. We will be able to prove it at least. But the separability is not true at all, because if this is equal to 0, okay, if, let me write, if, so integral of fp d mu equals 0, what we know is that this implies that fp equals 0 mu almost everywhere, but this does not imply that f, so this implies also that, this implies also that the absolute value of f is equal to 0 mu almost everywhere. That's not the problem. P is not the problem here. It could be p equals 1. The problem is that then this does not imply that f is equal to 0 everywhere. This is not true. Okay, so we're facing a problem here, and how do we circumvent this this effect? Well, by introducing an equivalence relation like this. So we'll say that f is equivalent to g with this symbol here, with this tilde, if f is equal to g mu almost everywhere. And in fact, we will not consider really functions, but equivalence classes of functions which are equal with one another, which are equal almost everywhere. The fact that they differ by a small amount, if you want, and I mean not a small amount, but they differ only on a small number of points from the point of view of the measure, is not so important in measure theory. So we will do just as if two functions which are equal almost everywhere are actually the same. Okay, that's roughly the idea. So we introduce this equivalence class here of f. So this is no longer really a function. This is an equivalence class. And this has important consequences that we will discuss further. And now, instead of calligraphic LP, we will define a new space, which is with a straight L here, LP, which is not a class, it's not a set of functions, but it's a set of equivalence classes. And these equivalence classes that we denote, so for now, just to emphasize a little bit, we denote this with a bracket, but then we will remove the bracket. But bear in mind that these are equivalence classes and not actual functions. Okay, so in some sense, bracket of f and f are identified, meaning that functions which are equal mu almost everywhere are considered the same. That's roughly the idea. And you see that if I do that, now the fact that this means that f is equal to 0, actually this is also true, that f is equal to 0 almost everywhere, mu almost everywhere. Well, in some sense, the fact that it's equal to 0 mu almost everywhere, that means that the bracket of f, the equivalence class of f, is just 0. Okay, it's the same as the equivalence class of 0 if you prefer. And so in this set, where you do not consider functions but equivalence classes, well, in that sense, you get the separability for LP straight. Okay, so now we defined what we will be able to prove that it's a norm. We defined this object here as the integral of the absolute value of f to the p and the integral to the power 1 over p. Okay, same, reasonably, I mean, same for the infinity norm, which is a bound on f mu almost everywhere. And this thing we will see, okay, it's not obvious, we will prove that this is a norm on LP, a proper norm now. Okay, so what do we need? Okay, the separability, thanks to this trick, is now achieved. So we have the separability, the homogeneity, I don't show it, it's obvious. Okay, so what we need is a triangle inequality. So one way to prove triangle inequality is via the Hölder's inequality. So I will not prove Hölder's inequality because it's in you can do it in the labs or by yourself. It's you have an exercise for that. But what does Hölder's inequality? So that's really an inequality that you need to be able to use. It tells you that if P and Q are between 1 and plus infinity, and that they satisfy this relation, then for any f and g which are measurable functions, you have this inequality that holds. Okay, the integral of the product, the absolute value of the product of f and g against d mu, is less than the p norm of f times the q norm of g. Okay, you see that in particular, if this is finite and this is finite, so all this is finite, this implies that fg is integrable. Okay, another consequence is the inclusion of LP spaces when the measure is finite. So I will just make first a remark concerning the Cauchy-Schwarz inequality, and then another remark on finite measures. So the Cauchy-Schwarz inequality, which is actually the case P equals Q equals 2. So it's a subcase, it's a particular case of Hölder's inequality, and it tells you that the integral of fg d mu is less than the integral of f squared d mu to the 1/2 times the integral of g squared d mu to the 1/2. Okay, that's called Cauchy-Schwarz inequality. And why? We will see why, because in fact this is the L2 norm. Okay, and the L2 norm. So it's very similar to the Cauchy-Schwarz inequality that you already know, but in a different vector space. And another remark that I want to make. So perhaps you can skip this slide if you want to go a little bit faster, because this is this is something that I will recall later. So don't bother too much if you want to go to the next slide. Is the following observation. So in the case where the measure is finite, okay, mu of E is finite, we have that if I have two coefficients P and let's say P prime smaller than P, of course this is always greater than 1. So if we have this, then LP of E is included. Actually, if the inequality is strict, or it can be, so it's included in LP prime of E. Right? And so why is this true? Well, of course, this is if I'm saying this here, this is because I can prove it as a consequence of Hölder's inequality. So let F be in LP of E. So then I want to prove that F, the integral of the power P prime of F is finite. So then the integral of F to the power P prime d mu, and I want to find an upper bound on this quantity which will be finite. So here I will use Hölder's inequality and I will apply it. So actually I will decompose it like that. So this will be 1 times the absolute value of F to the power P prime. And the exponent that I will use is P. So the P in the previous slide now is actually P over P prime, which by assumption is bigger than 1. And its conjugate exponent, so the Q in the previous slide, will be 1 over 1 minus P prime over P, which is equal to P divided by P minus P prime, if I'm correct. Yes. Okay. So this is less than the integral of 1 to the power P over P minus P prime d mu. So this is actually the P over P minus P prime norm of 1. So here I should have P minus P prime over P times the integral of F to the P prime to the power P over P prime d mu P prime over P. So actually this is actually the LP norm, because all the exponents simplify. So it's F, it's the LP norm to the power P prime, but this is finite anyway. And here, this quantity inside the parenthesis is mu. It's equal to, so it's equal to the integral of 1 d mu, which is mu of E by definition. Okay, this is an integral over E, so it's mu of E. So all this is less than mu of E to the power P minus P prime over P times the LP norm to the power P prime. And all this is finite, okay, by assumption this was finite. So F is in LP prime. Okay, so you see the assumption here is crucial to deduce some inclusion property between the LP spaces. Otherwise, in general, this is not true. Right? And so here will be the triangle inequality that we were needing. So I will not do the proof right now. I will do it at the end of the video, so that it's not an essential proof of these lectures. So if you want to have a look at it, you can wait until the end of the video. Otherwise, you can just keep it. Okay, so proof at the end of the video. But Minkowski's inequality is nothing but the triangle inequality for this object, okay, this double bar P, which turns out to be a norm then. Okay, so proof at the end of the video. Okay, but this is very important. So remember that the proof follows. It's a consequence of Hölder's inequality. And come on. Okay, so the proof at the end, and the immediate consequence of that is this space, which we already know to be a vector space, is actually a norm vector space. Okay, this object is a norm, so that's very nice now to be able to work in norm vector spaces. You see why in lecture 1 and 2 we focus so much on norm vector spaces. And actually, this for any p in 1 infinity, this norm vector space is complete. So this norm defines a distance for which all Cauchy sequences converge. So I'm not proving this at all. This is a bit too long. We could do it, but it requires some time. Right. Another interesting fact, but which is, I mean, there's no much mathematics needed to compared to previous results, is that actually, if I look at the particular case here, p equals to 2, well, this defined now, we will have now a Hilbert space for which inner product, well, the one that is given here, and you see that, okay, remember, if, okay, so check that the mapping which takes f and g and spits out the integral of f g d mu is an inner product. So that's an exercise for you. But once you've admitted this fact, well, it's not difficult to see that we have a Hilbert space, because observe then that so if this is an inner product, the norm associated to it is f squared equals f against f, which is the integral of f squared d mu. Okay, and this is precisely what we call the L2 norm of f, well, squared. Okay, because I didn't take the square root, right? So this is an inner product. This corresponds to the L2 norm. So we know that L2 with the L2 norm is complete. We have an inner product. Okay, so our pre-Hilbert space is complete, and therefore it's a true Hilbert space.